Welcome back to our deep dive, into the world of computer science, the field that's always pushing the boundaries of what's possible. Today we're going to be focusing on neuromorphic computing.
Okay.
You've sent in some intriguing research about brain-inspired hardware and neural systems,
Yes.
and I'm really curious to unpack all this with you.
It's a field that holds immense potential. For decades, the idea of building computers that function like the human brain has been a sort of holy grail for computer scientists.
Yeah, and what stands out to me from your research is how neuromorphic computing is blurring the lines between biology, mathematics, engineering, and physics. It's not just computer science anymore. It's a fusion of disciplines.
Precisely. It's this interdisciplinary nature that makes it so compelling and, frankly, quite challenging. We're not just trying to build faster computers. We're trying to understand the very principles of intelligence and replicate them in silicon.
Wow, it's like reverse engineering the most complex machine we know of, the human brain. Now, your research highlights some fascinating milestones in this journey. Can you walk me through some of the key moments that paved the way for where we are today?
Absolutely. One of the earliest breakthroughs came in 1981 when Carver Mead at Caltech created the first analog silicon retina and cochlea. He essentially replicated the senses of sight and hearing in silicon. It was a revolutionary achievement that demonstrated the potential for mimicking biological systems.
I find it incredible that this was happening back in the early 80s. It really highlights how long researchers have been pursuing this vision of brain-inspired computing. What happened next?
Fast forward to 2009, and researchers at Stanford University unveiled NeuroGrid. The system took a different approach, focusing on mimicking the way neurons communicate with each other, using an analog synaptic approach. It was a significant step towards building systems that could learn and adapt like the brain.
So early on, we had these pioneering efforts, but as your research indicates, collaboration became increasingly important to push the boundaries further. I'm thinking specifically about the Human Brain Project.
Yes. The Human Brain Project launched in 2013 with a truly ambitious goal to simulate the entire human brain. It was a massive undertaking involving hundreds of scientists from around the world. While it's faced its share of challenges, it underscores the scale and complexity of trying to decipher the brain's secrets.
It's mind-boggling to imagine the level of collaboration required for such an endeavor. So from these early pioneers to large-scale collaborations, the groundwork was laid. But when did industry really start to take notice and invest in this technology?
A pivotal moment came in 2014 when IBM introduced its TrueNorth chip. This marked a turning point where the industry began to recognize the potential of what they called aha computing. It signified the ability of these brain-inspired systems to solve problems in a way that mimicked the brain's sudden insights.
The term aha computing perfectly captures the essence of what makes the brain so remarkable. Those moments of sudden understanding, it sounds like IBM's TrueNorth chip really opened the floodgates for further innovation.
Absolutely. Other major players like Intel followed suit in 2018. Intel released its Loihi chip, which found applications not only in traditional computing but also in areas like robotics and even smell recognition. It demonstrated the versatility of neuromorphic chips in mimicking a range of sensory capabilities.
From replicating individual senses to developing chips capable of mimicking more complex brain functions, the progress has been astounding. But it seems like the advancements didn't stop there. Your research also mentions BrainChip and their work on energy efficiency.
Yes, in 2020, BrainChip introduced the Akita processor. It boasted remarkable energy efficiency, surpassing conventional computing solutions by a significant margin. This development highlighted another key advantage of neuromorphic computing, its potential for sustainability.
So we've gone from replicating individual senses to building entire chips that operate more like a complete brain, and now we're seeing a focus on making them incredibly energy efficient.
It's truly remarkable how far this technology has come in just a few decades.
It really is, and what's even more exciting is that we're just scratching the surface of what's possible. I can't wait to dive deeper into what the current landscape of neuromorphic computing looks like and explore where this revolutionary technology might be heading next.
Welcome back to our deep dive into neuromorphic computing. It's fascinating to consider how this technology is fundamentally changing our approach to computation, taking inspiration from the intricacies of the human brain.
It's a real paradigm shift. Last time we walked through the historical evolution of the field, highlighting key breakthroughs and the growing industry interest. Now I'm curious to delve deeper into what makes neuromorphic systems so unique. What are the fundamental differences between traditional computers and these brain-inspired systems?
One key distinction lies in the architecture. Traditional computers are based on the von Neumann architecture, which separates the processing unit, the CPU, from the memory unit. This constant shuttling of data between these units creates a bottleneck limiting speed and efficiency, particularly for complex tasks that require a lot of data processing.
So it's like having a library where the reading room is miles away from the book stacks. You'd spend more time traveling back and forth than actually reading.
That's a great analogy. Now, imagine a library where the books are readily available right at your fingertips in the reading room. That's more akin to how the brain operates and what neuromorphic computing aims to achieve.
No more wasted time fetching data. Everything is integrated. How do neuromorphic systems manage to pull off this integration?
They do it through a combination of innovative hardware and software designs. Neuromorphic chips are built using artificial neurons and synapses interconnected in a way that mirrors the neural networks of the brain.
So instead of distinct processing and memory units, these chips have everything intertwined. Just like in the brain, it's a complete rethinking of how we structure computation.
Precisely. And this integrated structure allows for massively parallel processing, meaning that many operations can happen simultaneously. This is a game changer for tasks that involve pattern recognition learning and adaptation things that traditional computers struggle with.
It makes sense. Our brains don't process information in a linear step-by-step fashion. We're constantly making associations, recognizing patterns, and adapting based on experiences.
Yeah.
It sounds like neuromorphic computing is enabling machines to do the same.
That's the goal. Another crucial difference is how these systems handle information. Traditional computers rely on digital signals representing data as discrete bits, ones and zeros, but the brain operates using analog signals, which are continuous and capable of representing a much wider range of values.
So if digital signals are like a light switch, either on or off, analog signals are like a dimmer switch, offering a spectrum of brightness.
Another great analogy in neuromorphic computing embraces this analog nature of the brain. Many neuromorphic chips utilize analog circuits for processing, allowing for greater efficiency and flexibility in computations.
Integrated processing and memory, massive parallelism, and analog computation, all inspired by the elegance and efficiency of the brain. It sounds like a recipe for incredible computational power.
It is, and as these systems continue to develop, they have the potential to revolutionize many fields.
You're right. But with all this talk about efficiency and processing power, I'm wondering about energy consumption. Our brains are incredibly energy efficient. Can neuromorphic computers keep up?
That's a vital consideration, especially with growing concerns about the energy footprint of computing. Traditional computers, especially those used for high-performance computing, can be incredibly energy hungry.
Yes. I've heard stories about supercomputers that require their own dedicated power plants. Not exactly a sustainable model for the future.
Exactly. Neuromorphic computing offers a far more sustainable path because these systems are modeled after the brain's efficiency. They can perform complex tasks using a fraction of the energy required by traditional computers.
So we're not just talking about faster, smarter computers, but also greener computers, a win-win for both performance and sustainability.
Absolutely. And this energy efficiency becomes even more critical as we move towards a world increasingly reliant on data. The explosion of artificial intelligence, the Internet of Things, and countless data-intensive applications demands a new approach to computing that can handle the load without draining our energy resources.
It seems like neuromorphic computing, with its roots in the energy-efficient brain, is perfectly positioned to meet that need.
Indeed, as research in this field accelerates, we're approaching a new era in computing, one defined by brain-inspired systems that are not only powerful and efficient, but also capable of learning and adapting in ways we're only beginning to explore.
I'm eager to delve deeper into specific applications where this technology is already making an impact. Where should we begin?
Robotics is a particularly exciting area where neuromorphic computing is showing great promise. Imagine robots that can navigate complex environments, learn from their experiences, and interact with the world in a much more natural and intuitive way.
It's a far cry from the rigid, pre-programmed robots we often see in industrial settings. How is neuromorphic computing changing the game for robotics?
It's all about giving robots a brain-like control system. Neuromorphic chips enable robots to process sensory information in real time, make decisions based on that information, and adapt their behavior accordingly.
So these robots aren't just blindly following a set of pre-programmed instructions. They're learning, evolving, and becoming more intelligent over time.
Precisely. And this opens up a world of possibilities, from self-driving cars that can navigate complex traffic scenarios to assistive robots that can provide personalized care.
It's fascinating to think that we could one day have robots working alongside us, not as mindless machines, but as intelligent collaborators. What other areas are particularly ripe for disruption by neuromorphic computing.
Another area that's generating considerable interest is edge computing.
Now, before we go further, can you explain what edge computing is? I've heard the term, but haven't quite grasped its full meaning.
Of course, edge computing essentially brings computation closer to where the data is being generated. Instead of sending vast amounts of data to a central cloud server for processing, edge computing devices process the data locally at the edge of the network.
It's like having a mini brain, right, with the actions happening. What are the advantages of that?
Several. First, it reduces latency if a device has to send data to the cloud and wait for a response. There's an inevitable delay. Edge computing eliminates that delay, which is crucial for real-time decision-making in applications like autonomous driving or medical monitoring.
So for situations where split-second decisions are critical, edge computing is essential.
Exactly. Another advantage is reduced bandwidth requirements. If devices are processing data locally, there's less need to transmit huge amounts of data to and from the cloud, leading to cost savings and improved network efficiency.
Okay, I see how edge computing can be beneficial, but how does neuromorphic computing fit into this picture?
Neuromorphic chips are ideal for edge computing devices due to their low power consumption and their ability to handle complex computations efficiently. This allows for the creation of edge devices that are not only powerful but also compact and energy efficient.
So we could have tiny brain-inspired devices embedded in everything from smartphones to self-driving cars, making them significantly smarter and more responsive.
Precisely. And these edge devices could even collaborate, sharing information and learning from each other, creating a distributed network of intelligent systems.
It's like a swarm of mini-brains working together to solve problems. An intriguing concept.
It is. And as the Internet of Things continues to expand with billions of devices connected to the Internet, neuromorphic computing at the edge will play a crucial role in managing and making sense of all that data.
This all sounds incredibly promising, but are there any challenges or limitations we should be aware of as this technology continues to develop?
Of course, while we've made remarkable progress, neuromorphic computing is still a young field. One of the biggest challenges is the sheer complexity of the brain. We're still deciphering its inner workings, which makes it difficult to create truly brain-like systems.
It's like trying to build a spaceship before we fully understand the laws of physics.
A perfect analogy. Another challenge lies in the need for new programming paradigms. Traditional programming languages and techniques aren't well suited for these brain-inspired systems we need to develop new ways of interacting with and instructing these computers.
So it's not just about building the hardware, it's about revolutionizing the software as well.
Absolutely, and this is an area of active research with scientists and engineers developing new algorithms, programming languages, and tools specifically designed for neuromorphic computing.
It sounds like there's still much work to be done, but the potential benefits make the journey worth it.
I agree. The pursuit of truly brain-like computers is one of the grand challenges of our time, and as we push the boundaries of this field, we're not only deepening our understanding of the brain, but also unlocking the potential for a new computing paradigm that could transform countless aspects of our lives.
I'm already eager to see what the next breakthrough will be, but I think we've covered a substantial amount of ground today. Perhaps this is a good point to pause our deep dive and pick it up in our next episode.
I agree. We can explore more specific examples and delve into the future directions of neuromorphic computing in our next installment.
To our listeners, thank you for joining us on this exploration of neuromorphic computing. We'll be back soon to venture further into this exciting frontier. Welcome back to the Deep Dive. We're continuing our exploration of neuromorphic computing, where the world of computer science is taking cues from the most powerful processor we know, the human brain.
Yeah, it's been an intriguing journey so far. We've discussed how this field is shifting away from traditional computer architecture, drawing inspiration from the brain's interconnected structure and its ability to process information in an analog way.
Absolutely. And we've explored how this brain-inspired approach is leading to advancements in robotics and edge computing. But it seems like the potential of neuromorphic computing goes far beyond those fields. Your research points to a revolution in how we approach data analysis, pattern recognition, and even machine learning.
That's right. These are areas where the brain truly excels, and it's fascinating to see how these principles are now being applied to the world of computing.
Let's dive into some specifics. Your research highlights image and speech recognition as areas where neuromorphic computing is showing immense promise. It makes sense, considering how effortlessly our brains can recognize faces, objects, and voices, something that's proven notoriously difficult for traditional computers.
Exactly. Conventional computer vision and speech recognition systems often rely on complex algorithms that are computationally expensive and require massive amounts of data, but neuromorphic systems can achieve similar, if not better results, using significantly less energy and processing power.
Because they're learning more like we do, right? By recognizing patterns and making connections.
Precisely, neuromorphic systems can be trained on vast data sets of images and sounds. They learn to identify key features and patterns, much like the human brain does this, allows them to recognize objects, faces, and voices with remarkable speed and accuracy.
So perhaps one day we'll finally be free from those frustrating moments of struggling with facial recognition technology that just can't seem to recognize us.
Let's hope so. But beyond improved accuracy, neuromorphic computing could unlock entirely new capabilities in image and speech recognition. Imagine systems that can understand emotions conveyed in speech or even detect subtle medical conditions from images.
Wow, that's incredible. We're talking about computers that not only see and hear, but can also interpret and understand the world around them, much like we do. What are the implications of this?
The possibilities are far-reaching. It could revolutionize fields like healthcare security and even human-computer interaction, for example, in healthcare. Imagine a system that can analyze medical images to detect early signs of disease far more accurately and efficiently than a human radiologist.
It seems like image and speech recognition are just the tip of the iceberg. What other applications are you particularly excited about?
One area that's particularly promising is drug discovery and development.
Now, I wouldn't have immediately linked brain-inspired computers with pharmaceuticals. Can you explain the connection?
Of course, developing new drugs is a complex and time-consuming process. It involves simulating the interactions of countless molecules to identify potential candidates, followed by rigorous testing in labs and clinical trials. It's a bit like searching for a needle in a haystack.
Oh, I can only imagine. And I'm guessing that's where neuromorphic computing can make a difference.
Exactly. Neuromorphic systems can drastically accelerate this process by simulating molecular interactions at incredible speed. And with remarkable accuracy, they can analyze vast data sets of chemical compounds and pinpoint potential drug candidates far more efficiently than traditional methods.
So it's like having a superpowered research assistant that can sift through mountains of data and guide scientists toward promising avenues for drug development.
That's a great way to put it, and this could have a profound impact on the development of new treatments for diseases like cancer, Alzheimer's, and a host of other conditions.
It's truly amazing to think that brain-inspired computers could play a role in developing life-saving drugs. It underscores the potential for this technology to improve our lives in countless ways.
Absolutely, and it doesn't stop at finding new drugs. Neuromorphic computing can also help personalize medicine by tailoring treatments to an individual's unique genetic makeup and medical history.
It's like having a doctor with an unparalleled understanding of your specific needs, able to prescribe the most effective treatment for you.
Precisely. It's all about using the power of brain-inspired computing to make healthcare more precise, effective, and personalized.
We've covered a lot of ground in this deep dive: robotics, edge computing, image recognition, drug discovery, personalized medicine. It seems like neuromorphic computing is poised to touch nearly every aspect of our lives.
It really is a transformative technology. While it's still in its early stages, the progress we've seen is remarkable. I'm incredibly optimistic about the future of this field.
As am I. It feels like we're on the cusp of a new era in computing. And to our listeners, thank you for joining us on this exploration of neuromorphic computing. We hope you found it as fascinating as we did. Until next time, keep those brains firing, and we'll catch you on our next deep dive into the world of cutting-edge science and technology.